Okay, so in this video we're going to think about an alternative viewpoint on principal component analysis. And we're going to think about it as a method that compresses a matrix in such a way as to minimize the reconstruction error of that compression. So, like in the first section here, we're going to assume that we've got data x1 to xn that are in Rp, but we're going to assume the data's been centered already here. Okay, so we're going to assume that x bar is 0. If it's not, just subtract x bar from everything. Okay, it's just to make the mathematics easier. So we've seen that PCA is the solution to this optimization problem. That for k equals 1 to r, we're going to try and find the vector uk that maximizes the variance of ukx, which turns out to be the same as maximizing uk transpose suk, but subject to the constraints that the u's are vectors of length 1 and that they are orthogonal to each other. So a different way of writing this, which hopefully you can see, is that it's the same as maximizing the trace of u transposed su subject to u transposed u equaling the the identity matrix, the R by R identity matrix, where U is P by R matrix. And the reason that's the same is that if you think about this, the trace of U transposed SU, well, if I write out what U is here, this will be the first vector U1 transposed down to UR transposed times S times U1 across to UR. So that is just the sum of k equals 1 to R of UK transposed SUK. Okay, so this maximization problem is the same as the problem above, although admittedly for the second problem we don't get the ordering, but we can order things after the event. But it's going to solve the same problem. We're going to end up with the same solution, that is u being the eigenvectors. So another way of thinking about this is to think about our data matrix X, which is x1 transposed down to xn transposed, and to think about finding the best rank R approximation to X. And you already know the answer to this is going to be the singular value decomposition, because we saw it in the previous chapter. But let's think about this and derive it in a different way. So one way to think about this is to try and find a P by R matrix U such that there exists yi in R such that xi is approximately equal to u yi. Okay, so this is a rank R model. If you think about it, think about this as a linear model. So we're going to model the data as f of y, which is uy. So u has R columns, y has R coordinates in it. So we're going to try and find a new coordinate y that is a linear combination of the u's, and we want this to be, we want to choose u and y in such a way that u of yi is approximately equal to xi. So we've got to find both u here and the yi's. So how can we choose the u's and y's? Well, one way to do it is to choose u and yi to minimize the sum of squared error. So to minimize the difference between xi and u yi squared. So we're using Euclidean distance, where I put the 2 there, and we'll use the square of it. Okay, so this is the sum of squared errors. Now if we write y to be the matrix y1 transposed down to yn, just like our data matrix X is, then we can see that this sum of squared errors is just the trace of X transposed minus uy transposed, all transposed, times X transposed minus uy transposed. Okay, so you have to stare at that for a moment to see that that's true. But once you can see that it's true, if you remember, the trace of a matrix transposed times itself is just a way of computing the Frobenius norm. So this is X transposed minus uy transposed squared. Okay, square the Frobenius norm. So another way of phrasing this again is to say we're trying to find the rank R matrix XR that minimizes the difference between X and XR, the original data matrix and XR, in the Frobenius norm here. Now, it doesn't matter if we transpose these, so this is the difference between X transposed minus XR transposed. Okay, it makes no difference at all. And all we've said here is that a rank R matrix is of that form. Is of the form uy for some u and some y. That's XR. If it's rank R, must be u, y, t for some P by R matrix u and an N by R matrix y. Well, we need to choose u and y here. So let's first think about how we choose y. Let's restrict u to be orthogonal. So u transposed u equals identity. So it's semi-orthogonal. Okay. And the reason for doing that is if u is our coordinate system, coordinate systems with non-orthogonal axes are really confusing. Okay. So we always use orthogonal coordinate systems. So let's restrict it to be orthogonal. So what we're doing here, how do we pick y? Well, we know from the section on orthogonal projection that to solve the optimization problem, if u is of the form uy, we want to minimize the error between x and u. So in other words, we want to project x onto the space defined by the columns of u. Okay. Then we set u equal to the projection matrix for u times x, and the projection matrix is going to be U transpose U inverse U transposed X. But U transpose U is identity, so this is just U transposed X. Okay. So we set, this is telling us that we must set Y equal to U transposed X. Okay. This is the coordinate of the orthogonal projection of X onto the columns of U, the column space of U. Okay, so we've seen that before in chapter 3. So what's left? We said we wanted to minimize X transposed minus U Y transposed. Okay, but we've just said yi had to be U transposed xi. So Y transposed, the matrix Y transposed is U transposed X transposed. Okay. So this is just X transposed minus U transposed X transposed for the Frobenius norm. Okay, so we know what Y must be. All that left is saying what U must be. The first thing to note is that the Frobenius norm isn't changed by transposing a matrix. So the Frobenius norm of A is the same as the Frobenius norm of A transposed. So let's transpose everything here. I'm going to make the maths a bit nicer. So this is the same as the Frobenius norm of X minus, now if we transpose this, we swap the order. So this is going to be X U transposed. Now the next thing to remember is that we can write the Frobenius norm as the trace of the matrix transposed times itself. So this is going to be X minus X U transposed times X minus X U transposed. So let's multiply out the brackets here, and let's remember that the trace of A plus B is the trace of A plus the trace of B. Okay, so we're going to get the trace here of X transposed X minus the trace of, if we transpose this, we're going to get U transposed X transposed X minus the trace of X transposed X U transposed plus the trace of U transposed X U transposed. Okay, I'm going to stop underlining my matrices. There's too many of them. Okay, everything's a matrix. Now then, what is this equal to? Well, this is the trace of X transposed X. Now, the other fact to remember is that the trace of A times B is the trace of B times A, assuming we can swap the order of A and B here. So in this first term, let's take this U to the right hand side. It's the right shape after all, so we can do that. So this is minus the trace of U transposed X U. Let's do the same here. Let's take this U transposed to this side. So this is minus the trace of U transposed X U. And finally, over here, let's take this U to the right. So this is plus the trace of U transpose X transpose X, U transpose U. So this is the trace of X transpose X. Now, these two terms are the same, so we've got two of them, and in here, this is going to cancel. This is going to be the identity matrix. So we get left with minus the trace of U transpose X, X transpose U. So what did we start with here? We started with this expression, X transposed minus our reduced rank matrix. So let's just rewrite that in. So this, remember, was the difference between X and XR. Okay, squared. Okay, yep, sorry, there's a typo here. These should have been squared at the start. It didn't make any difference until this line here needs to square for this third equality. Okay. So, minimizing the reconstruction error, or the error in approximating X by our rank R matrix, XR, is equivalent, you can see, to maximizing, well, this term here, the trace of X transpose X doesn't have U in. So it's equivalent to maximizing this term because of the minus sign. So maximizing the trace of U transposed X U. So choosing U to minimize XR, which was X U transposed, we said. Okay. So choosing U to minimize this reconstruction error is the same as choosing U to maximize this trace term. So, but this you'll recognize as n times the trace of U transposed sample covariance matrix times U. So this was our PCA problem. Okay. So approximating a matrix by a rank R matrix is just exactly the same problem as doing PCA, principal component analysis, where we're trying to maximize the variance. Okay. So whether you are finding a rank R approximation or doing PCA, they're the same problem. Okay, so this is a different way of thinking about principal component analysis.